Hi, I'm Harry Felton from the Design and Manufacturing Futures Lab at the University of Bristol, and I'll be talking you through my paper, Looks Like But Does It Feel Like? Investigating the Influence of Mass Properties on User Perceptions of Rapid Prototypes. As the title suggests, the paper aims to investigate whether the mass properties of a 3D printed prototype affect how a user perceives the prototype. In the coming slides, we'll briefly look at a little background to MEX, how the study was undertaken, and finally, summarise the results. MEX offers a cheap, easy-to-use method of fabrication for prototypes that is able to relatively accurately replicate design geometry with little user input. The parts produced using MEX are normally formed of an outer shell, shown in grey in the top right image, and a lower density infill pattern, shown in white, to reduce print time and cost whilst maintaining suitable part structure. Similarly, to save cost, parts are generally printed in a thermoplastic material, often PLA, ABS, or nylon, when they would normally be fabricated using composites or metal, or have other components incorporated into their structure. This often leads to poor matching between designed and printed mass properties. It is hypothesized that this poor matching may be problematic, with the mass properties thought to be an important part of the perception a user develops of a product. This is briefly discussed in work published by Hewden Hill that used a pizza box with a brick in it to resemble a laptop in a user study, though this work stopped short of discussing any results. As such, it was thought a more detailed study would be beneficial in investigating this hypothesis, with results demonstrating how the effect of mass changed user perceptions. This brings us on to the main work completed for this paper, a user study. The study was designed around the Ultimaker hand drill that had been modified to provide pockets in the upper and lower sections where the motor and battery would normally be placed. 3 artifacts were fabricated using PLA, lead pellets, and iron filings, with the production of drill 3 shown in the top right of the slide. All the drills used the same print settings and materials to ensure they looked the same. Drill 1 was an unmodified drill, Drill 2 had mass added to the base of the drill, and Drill 3 had mass added to the top of the drill. This was done such that the mass and centre of mass position, relative to the height of the drill, were different for each artifact. The students were then asked to undertake an activity with the drills that had been fitted with 8.5mm drill bits. This involved pushing the drill bit through 6 10mm diameter holes in the sheet of acrylic in a predetermined, consistent order. The sheet had obstacles added to it to force each participant to turn the drill to complete the objective. To ensure the task was performed with an unambiguous objective, a prize was awarded to the participant who completed the task fastest with a single and all 3 drills. After completion of the task, the participants were asked to fill in a survey with the 3 questions shown on the slide. The participants initially answered these questions without any input from the interviewer, but their answers were then discussed to understand meaning. This provided the results shown here. Before discussing the results, it should be noted that the order the drills were used in was selected by each participant and was nominally random. Though drill 2 was used slightly more often than any other, there is no obvious correlation between the order the drills were used in and the answers the participants gave to the questions. As can be seen from the table, drill 2, the drill of the median mass and lowest centre of mass position, was the preferred design, based on mean score and the number of times selected as the preferred design. Though it was unimportant which drill was considered best for this work, it was important to note that participants were able to score the drills differently and select a favourite. This is important as this demonstrated that variation in mass properties could significantly affect how a user perceives otherwise identical prototypes. The next set of results, presented in the figure, look at how the participants recognised each mass property in questions 2 and 3. As can be seen, mass was easily the most recognised property, with balance and moment of inertia being recognised less often, in that order. It was thought that this was because these properties were more poorly understood than mass by the participants, though it is also recognised that mass was likely to have a more significant effect than moment of inertia for the task laid out. It should also be noted that although the task was timed, the performance of each drill in the task did not show strong correlation with the scores the drill received on a case-by-case basis, highlighting that mass properties were obviously an important consideration for the participants. And so, this brings us on to our conclusions. The 3 main takeaways from this paper were firstly, that all participants were able to clearly recognise differences in mass. Several could recognise balance variations and a few recognised different moments of inertias. Secondly, that the participant scores appear to have been more heavily affected by the mass properties of the artifact over their performance with the artifact. And 3, for work not shown in this presentation but discussed in the paper, the industry recognised that mass is important for user interaction but can also be a design driver in its own right. So thank you for watching this presentation. The paper is available open access as part of the Design 2020 proceedings, and I would invite you to read more about this work in the publication.